When we talk about equilibrium, we're talking about things that we can go in one direction and then they can go back in the other direction. Takes a certain amount of time to get our reactants to convert to products, and then if our products are interacting, to convert back to reactants. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So a lot of the reactions in our bodies are at an equilibrium. They're reversible. So when we get this constant concentration of both, so the rate of the forward equals the rate of the reverse, the concentrations aren't equal, but the rate of making the concentration of one is equal to the rate of making the concentration of the other. So the concentrations are stable, they don't change anymore. We get what we call an equilibrium. We can calculate this equilibrium constant. It is given by the letter K. Okay. When we look at K, we can look at the magnitude of K. If K is greater than 1, we favor products. If K is less than 1, we favor reactants. And if K is equal to 1, we have an equal mixture of both. We can write what are called these K expressions, where we look at a balanced chemical equation and we put the products over the reactants raised to any coefficients. And so we get a ratio there. And so at equilibrium, the ratio is constant. If I perturb any part of that equilibrium, if I say remove a product, I need to get back to that same ratio. So my system will adjust to get back to that ratio. If I take out a reactant, if I flood it with something extra, my system will be out of equilibrium, and then it will readjust until it gets back to equilibrium and back to that same ratio. Okay. Again, we can look at our equilibrium constants, the magnitude of which gives us an idea of what is favored. So again, at a small k, what we have is reactants favored, a large K, products favored, and then if we have what is called an intermediate K, then we'll have appreciable amounts of both at equilibrium. All right, so you can see here, large K. All right, you can see what the picture of my reactant molecules look like and the product molecules looks like. And then this box is the reaction at equilibrium. And so you can see we have a whole bunch of our products. So again, this is product favored. Okay. Okay, small k. All right, so here are my reactants. There's my product, and then at equilibrium, you can see I mostly have reactants. Again, this is at equilibrium, and then this is reactant favored. Okay. So what we consider a small k is if there's an order of magnitude less than 10 to the negative third. What we consider a large K is an order of magnitude greater than 10 to the positive third. So here's a question. We've got this receptor, okay, and we've got this molecule, epinephrine. So it binds to this beta androgenic receptor. Okay, that's where you get that heightened energy level. Release of epinephrine from the receptor has a K value of 5 times 10 to the negative 6th. Okay, I've got a solution of epinephrine with that beta androgenic receptor. Do we prefer to stay bound or free? All right, so we're saying the release has a small K value. So basically, the reaction we're looking at is bound back. Goes to released. Okay, we've got a K value here, 5 times 10 to the negative 6th. So it's really small. Small k is reactant favored. If our reactant is the bound version, it's going to prefer to stay bound. Okay, so this is our reactant. All right, and so small k, reactant favored. Therefore, bound is favored. All right, so that is how we assess the magnitude of K. Now what we can do is we can look at what is called Q. Okay, Q versus K. Q looks exactly the same as K. It's the same products over reactants ratio. What I can do is, if I can get a snapshot of the concentrations of everything at any point along the way during the reaction, I can calculate Q. If I can then compare Q and K, if Q is equal to K, we're at equilibrium. If Q is less than K, then we are going to be making product. If Q is greater than K, we'll be making more reactants. Okay? And so we can look at it this way. Q is greater than K, or K is greater than Q. I'm going to form products. K is less than Q. I'm going to form reactants. And when they're equal, we are at equilibrium. And then I can look at thermodynamics versus kinetics. Thermodynamics is that relative energy of our reactants with respect to products. In order to get a reaction to go, we have to get over the activation energy. Kinetics is how fast something goes. And so if I need more activation energy, if I have a higher energy barrier, then it's going to go slower. Okay? The overall energy can still be the same. But if I have a higher activation energy, then it's going to be much higher to get the reaction to go. Because if you think about it, like if I need this much energy to go versus this much energy, okay, my activation energy up here, not as many of my reactant particles are going to hit that minimum energy threshold than down here. And so what we can do is we can do something called adding a catalyst to our reaction. A catalyst just provides a different pathway. It'll lower that barrier. It'll lower the activation energy. So then we can get the reaction to go faster. The end result's still going to be the same. We're still going to make the exact same amount of product. And we're still going to get to the exact same energy state. We're just going to do it faster.